Hi there, this is an extra video to go through the hypothesis testing examples that are in the activity or participation worksheets. This is probably the hardest topic in the class, so I wanted to have a video also to go through these examples. One recommendation is to try a step, pause the video, like try a step, then watch the video, try a step, then watch the video. Keep pausing it like that. Maybe you watch this first example all the way through and then you try that on the second two examples. So I have the key or the solutions pulled up here, and I'm going to be able to draw on this with my little pencil. So we've got the 4 steps up at the top here, and you don't have to label these 1, 2, 3, 4 as you go. I'm just doing that to help you get used to the process. And it's kind of like training wheels, and you can remove that if you want to. So the first step is we're going to write our null and alternate hypotheses. And then we're going to check the conditions. And the drawing can either go up here or down here. Either the drawing can go in step 2 or 3, depending on how you do it. I think I've actually drawn it more in step 3. Then we're going to calculate our test statistic and our p-value. And then it's really important to write the conclusion out in context. Okay, so let's go through each of these. This one is a company is concerned that too few of its cars meet pollution standards. So too few kind of sounds like less than or a left tail test, but let's take a look. They want to test whether less than 80% of their fleet meets emission standards. They measure a random sample of 500 vehicles and 385 meet the standards. Is this evidence that too few of its cars meet the standards? Okay, so when we're writing our hypotheses, I always look for the alternate first because that has to do with the claim. So when it says test the claim that, or is this evidence that, that's our alternate hypothesis. So it often comes last. This very last sentence is the claim. Well, actually, it's also the first. They want to test whether less than 80% of their fleet meets emission standards. So actually, it's the first and the last in this case. So our alternate is that P is less than 80% or less than 0.8 or 0.80. You could also use this last sentence. Is this evidence that too few, meaning less than 80% of its cars, meet the standards? Now this number is also called P0. That's our baseline, what we consider for our null. It's sort of the status quo, or what we consider to be already true. So if our alternate is less than 80%, our null is going to be equal 80%. The null is always equal, and then the alternate is either less than, greater than, or not equal. Okay, so then our next step is to write the conditions. Okay, so remember our conditions are independence and 10%, randomization, and success failure. So independence, we want to make sure the vehicles sampled are independent from each other in emissions, different models, years, etc. Also 500, which is our sample size, must be less than 10% of all the cars in the fleet, in the population, in other words. Do we have random sample? Yes, they did state that. And then we need to test the numbers for our success failure condition. That's n times p and n times q. So our n is 500 and our p is 0.8 from our p0. And our q is 1 minus p. So if it's 80, 20, 60, 40, and so on. So our NQ is 500 times 0.2. So we get 400 and 100, so well above the 10. Now, this is a common thing to look out for. We use P0 here. We don't use P hat. So we will talk about P hat in just a minute, but P hat comes from our data. P0 is what we're testing. So keep in mind that we set up hypothesis test based on the assumption that the null is true. So that's why we're using 0.8 all throughout here. So we're setting up our test based on 0.8. Okay, and then we're going to see what happens with the null. Okay, now I didn't test what happens when I scroll. Okay, good. I was worried that my drawings weren't going to scroll. Okay, so now we're ready to move down to step 3. Here's a little summary that we have a left tail test, and we reject the null if the p-value is less than 0.05. So this is alpha, or our significance level. So many little pieces to this. So small is significant. So if our p-value is less than alpha, or our significance level, then we reject the null. So let's calculate our p-hat. This comes from our data, and that is 385 out of 500 meet the standards. Okay, so we have 77% meeting the standards. Now that is less than 80%. The question is that significantly less? Or is it just due to chance? Because this 500 is going to be different than this 500, or another 500, or another 500. Is it just that we got one, higher or lower just due to chance? Or is this significantly lower than 80%? So that's why we have done our sampling distributions, so that we can find probabilities using the normal distribution and figure out how likely is it to get a p-hat of 0.77 if the null is true, if it's really 80% that don't meet the standards. Or sorry, that do meet the standards. A lot of negatives in this one. So our test statistic, that's our z-score. That's our next step. I'm just going to switch over to the notes for a second here. Show you the formula. So the formula is p-hat minus p0 over the square root p0 q0 over n. Now this is a z-score. So we're saying how many standard deviations is p-hat from p0? And remember how I talked about setting everything up based on the idea that the null is true, that p0 is the value. That's why we use p0 in our standard deviation, not p-hat. So with our test statistic, we're saying how many standard deviations away from the mean is p-hat? Okay, so in our example here, we have 0.77 minus 0.8 divided by the square root 0.8 times 0.2 over 500. And this is negative 1.6771 standard deviations. That's our z-score. Can't really write with the mouse, so I'll try not to write too much with the mouse. Okay, now this is where it's nice to have a picture. You can just do a sketch by hand if you want. I put this in from Online Statbook because it's kind of nice to see. Okay, here's 1.67 to the left or below the mean. And this is our area here. Okay, so this is our z-score or test statistic. And then the probability is our p-value. Since I can't write, let me just one arrow. Okay, so our p-value, this is where we put it into Online Statbook. We put in 0, 1 because z-score has a mean of 0 and it goes by ones. 1 standard deviation from the mean, 2 standard deviations from the mean, 3 standard deviations from the mean. And here we're 1.67 below, and the probability of getting that, even though it looks pretty big, is 0.0468. So it is actually less than 0.05. So we're saying if the null really was true, it's fairly unlikely to get a sample where we have 77% that meet the standards. So we reject the null and we have evidence for the alternate. So kind of wrote this out here with a p-value of 0.0468. The result is statistically significant. There is evidence that too few of the cars meet emission standards. Okay, we'll go through this 2 more times, so hopefully it'll be get more and more familiar each time. The other piece of this is comparing the p-value method with the confidence interval method. And they can give opposite results or the same result. It depends on the situation. So what we do is we also make a confidence interval. And so to save you time, I have given you the interval already so that we can just focus on the conclusion part. But you would find the confidence interval the exact same way that you did in the previous module, or maybe it was in this module, depending on the term. So if we used p hat, so our 0.77, to make a 95% confidence interval, we would get 0.7331 to 0.8069. Compare this with p hat, or sorry, compare this with p0. Does the confidence interval support rejecting or failing to reject the null? Okay. So in this case, our 0.80, it's barely inside, right? It's close to the edge, but it is inside. So the null value is within the confidence interval. So that supports the null value. 80 is in here, so that supports the null, which would mean not rejecting the null. It's a double negative. So in our p-value method, we rejected the null, but the confidence interval actually gives us the opposite conclusion. It supports not rejecting the null. So in this case, the two methods give different results, but sometimes they will agree with each other. And the main difference is, you probably remember from the confidence interval formula that we use p hat in our square root, whereas in the hypothesis testing, we use p0. That's much the main difference there. Okay, go ahead and pause the video if you want to try the next example on your own, or if you want to watch it, totally up to you. Okay, so let's go through the next one. Using our data set, so we're going back to the people killed by the police. Test the claim that there is racial bias in police shootings. But what does that mean? Could be a lot of things that means. Specifically, test whether the percentage of Black people shot by the police is greater than 13.4%, which is the demographic percentage for Black people in the US. Okay, so remember, if there was no racial bias, we would expect the percentage of Black people shot by police to be about the same as the population percentage. And we would expect that for all races and ethnicities. So we're going to test, is the percentage of Black people shot by the police greater than the actual demographic percentage? Okay, and then we did this in an earlier module. We calculated the sample proportion, or the proportion in our data set. There were 1,593 Black people shot by the police out of 77,232, and that comes out to 0.2203. Okay, obviously that is greater. What we want to know is, what's the chance of that happening, and is this significant? Okay, you might have an idea about that already. So let's write out our hypotheses. This time, this is a right tail test, or greater than, because we're testing something as greater than. So our alternate is p greater than 0.134, and our null is always the equal, and the number is the same. Okay, it's the sign that we're testing, really. Okay, so let's go through the conditions for this one. Again, same conditions: independence, 10%, randomization, success, failure. Okay, do a little memory trick with those. So independence, if we consider the population, okay, so this is where the conditions are tricky on this, right? Because at the beginning of the term, we said this is a population, because we're trying to capture all the people killed by the police. But now we learned the conditions, and that doesn't really meet the conditions. So what if we thought of it as the population to be all the people who have encounters with the police, but some people get shot? That's another way to look at it. Those shot could be a sample who are independent from each other. I'm a little worried about this independent. Maybe they're independent, maybe they're not. So the conditions, sometimes it's good to question the conditions for sure. What we would need for the 10% condition is the 5,300, oh wait, not the right number. This is a number from the previous data set. The 7,232, I'll fix that. The 7,232 would need to be less than 10% of all those who had encounters with the police during those years. I think that would be fair to say. So is it a random sample? I don't know. That's questionable. We can still do the success failure condition, and that is the number of successes. So when we have the numerator, that turns out to be n times p turns out to be the numerator. You could still do 0.2203 times 7232, but you'll get back to 1593. And then the complement of that, the rest of the people, is also greater than 10. Okay, even if we have questions about the conditions, we're still going to do the math just because it's good practice. Okay, so this is, just to summarize, this is a right tail test, and we're going to reject the null if the p-value is less than 0.5. That's our significance level. This direction never changes. Smaller is always significant. So regardless of which way the test goes, we always reject if the p-value is smaller than alpha, or the significance level. Okay, so here's our p-hat, which we were given as both a fraction and a decimal here, 0.2203. So what we want to know, remember, p-hat comes from our data, and we want to know what's the z-score, or test statistic of this value. How likely is it that that happened or could happen? And so we want to know how many standard deviations from the mean is this value. So we use our z-score formula, p-hat minus p0 divided by the square root of p0 q0 over n. Okay, so we use our 0.2203 minus our null value, 0.134. And we use that again, divide by the square root, 0.134 times 1 minus that, which is 0.866 over n, 7232. And it turns out to be 21.5 standard deviations away from the mean. So you probably know that that is extremely unlikely. So even if, let's say, our conditions aren't quite met, it seems pretty clear that the percentage is larger than the population percentage. So I made a graph, but of course you can't even see any area because 21.5 standard deviations above the mean is like way over across the room. It's really far. This is only 3. So 7 times this amount, 0 to 3. It's way over to the right. Okay. I see I forgot to change my sample size here again. The labeling here is optional, but if it helps, these are the z-scores of proportions of people who are shot by the police. And here we're talking about Black people shot by the police in our sample size of 7,232. This would be like all the random samples of that size and the z-scores. Okay, so our p-value, what's the chance of getting that test statistic? That's 0. There's no way. If you put that in an online stat book, you're going to get 0 because you're so far away from the mean. So this is significant. Reject the null. Okay, so we can write out our conclusion. With a p-value of 0, the result is statistically significant. There is evidence, or I said extremely strong evidence, that Black people are shot by the police at a higher rate than the population. Okay, let's do the same comparison with the confidence interval and see if they agree or disagree in this case. So if we used p-hat to make a 95% confidence interval, we would get 0.2107 to 2299. Okay, that makes sense because it's right around p-hat, which was 0.2203. So compare this with p0, or the null hypothesis. Remember, that's our population, 0.134. Does the confidence interval support rejecting the null or failing to reject the null? Okay, so 0.134 is not in this interval, right? Not even close. The null value of 0.134 is way below the confidence interval. The confidence interval supports rejecting the null. So in this case, they both give the same result. They both say to reject. This is pretty clear evidence. Okay. Okay, one more. Again, if you want to try it, go for it. This one, I wanted to do an example of a right tail, a left tail, and a two-tail. So there is one thing different about a two-tail test because it has both tails. So let's look at this example. I won't show the hypotheses yet. In 2019, the poverty rate in the US was 10.5%. A local official wants to test whether their county has a different poverty rate than the rest of the US. In a random sample of 2,000 county residents, 9.3% were below the poverty level. Okay, so you might notice something different here, which is the word different. It doesn't tell us which direction, does it? That means we're going to use a not equal. So not equal goes with the two-tail test. It's either direction. It can be above or below. It's not specified. Okay? So here's what our hypotheses look like. So our alternate is P is not equal to 0.105. And the alternate is just like the others, it's equal P0. Okay, so same conditions. Independence, 10%, randomization, success failure. We need to make sure the people surveyed are independent from each other in income. We need to do our random sample appropriately for that. 2,000 must be less than 10% of all the residents in that county. We need a random sample, which sounds like we do have. And success failure, N times P and N times Q. So, I see I copied from a previous, sorry, that is really confusing. So I copied from a previous example. Oh yeah, this isn't even right. I thought I changed this, fixed this one already. Let me type it out. Type it. So our N is 2,000. No, it's not. That is not really working. Okay, I will fix this and repost it. So it should be 2,000. So our N here is 2,000. And our P is 0.105. Sorry about that. And so because this is 2,000, I'm pretty sure it's going to be greater than 10. And then N times Q would be 2,000 and then 1 minus 0.105. Okay, so those should both be greater than or equal to 10. Luckily, I see the next part is correct. So just to summarize, we have a two-tailed test, and we're going to reject the null, as always, if the p-value is less than 0.05. Unless we're given a different significance level, but if we're not given one, we assume that that's the value. That's the most commonly used. Okay, so our p hat, now this is where we go back to the data. 9.3% were below the poverty level. So our p hat is 0.093. Okay, so now we want to know how likely is that to happen? How many standard deviations above or below the mean is that? So we do 0.093 minus P0, 0.105, over the square root of 0.105 times 0.895 over 2,000. Okay, these are correct. And that turns out to be negative 1.7506 standard deviation, or Z-score. It's below. Another double check here is because we're below the mean. Remember our p is 0.105. This is less than that. So we should get a negative z-score. If it was to the right, we should get a positive one. So the thing that's different or unusual about a two-tail test is we go to both tails. So if it's, you can, sometimes it's confusing to know which way to go in online stat book. You're always going to go toward the tail. So we got the -1, so that means we're going to go less than. If you got a +1, then you would go to the right because it would be above the mean. So you're always going to go in the direction of the tail. And then we have two tails, so we multiply our probability by 2. You're going to just put in 1. So if we got the -1, so that's this area right here. Instead of also figuring out the other one, we're going to use symmetry because they're the same and multiply it by 2 to get both tails. Oh yeah, I see. I didn't even, I forgot to adjust that. That's the missions. Okay, so our p-value is 2 times the probability. So you would put this on an online stat book, 0, 1, and less than -1.7506. It came out to 0.04, so 2 times that is 0.08. So that is not less than 0.05, so we fail to reject the null. So this is fairly common to happen just due to chance. Now notice if it was a one-tail, it would have been significant, but it's a two-tail. So it's better to specify a direction in advance. You can get away with a smaller p-value that way. Or I should say if you do a two-tail test, it doubles your p-value. So you really have to be within half of that. Okay, so here's the conclusion. With a p-value of 0.08, the result is not statistically significant. There is not enough evidence that there's a different poverty level in the county than the rest of the US. And I kind of said this already. Note, if this was a left-tail test, it would have been significant. That's the drawback of the two-tail test. It doubles your p-value. Okay, on this one, I asked you to create the confidence interval. So if you want the practice, you can go ahead and do that. Otherwise, I've got it figured out for you here. Now, remember we used p hat. So our p hat is 0.093. Oops, I'm at the end of my document. So p hat plus or minus z star times the square root of p hat q hat over n. Okay, so we've got 0.093 plus or minus 1.96 for 95% confidence times 0.093 times 1 minus that over 2,000. The margin of error is 0.0127. That's pretty small because it's a good sample size, 2,000. So it looks like about 8% to almost 10.5%. So let's check our P0 was 10.5 or 0.105. Is that inside? Oh, again, it's just barely inside. The null value of 0.105 is inside the confidence interval. So when the null is inside, that's evidence for the null or failing to reject the null. In this case, the two methods give the same conclusion. So we failed to reject, and here we also failed to reject. So we didn't have significant statistically significant evidence here. Okay, well, I hope that helps. If not, feel free to contact me. We can work through office hours. There are just a lot of pieces to this, and there's also a lot of p's, right? There's p0, there's p hat, there's the p-value, which is a probability. So I think if you remember, the p-value is a probability of getting p hat, then that might help. There's a lot of p's, and there's a lot of components. So I will update this and post it along with this video, and I hope that helps, and I hope to see you soon. Bye-bye.